Hello, my name is Josep Laborda, co-founder and CEO at Factual. The paper I'm presenting today is framed in the context of the ARIADNA project. ARIADNA is a project funded by the European Union Agency for the Space Program under a Horizon 2020 grant. The high-level objectives of the project are to raise awareness about the technological enhancements of Galileo and the expected benefits and market perspectives in public transport and urban mobility, to build the capacity of urban mobility stakeholders, supporting their decision-making and ability to integrate Galileo in the urban mobility context, and last but not least, to facilitate Galileo deployment in public transport and urban mobility applications and services by creating concrete business opportunities between public transport and urban mobility actors in Europe and at global level. ARIADNA brings in a well-balanced consortium of 5 partners from 3 countries: Factual, a foresight, innovation and strategy firm focused on mobility with headquarters in Barcelona and coordinator of the ARIADNA project; the UITP, the International Association of Public Transport, who are responsible for engaging public transport authorities and operators with the project; Pildo Labs, an engineering company based in Barcelona, who provide technology insight on global navigation satellite systems, GNSS; the UPC, Polytechnic University of Catalonia, one of the most renowned engineering universities in Europe, that in ARIADNA bridge the academia world with the industry, particularly by managing the Space for Cities Forum; and Auxilia, an agency based in France, expert in analyzing socio-ecological transitions and sustainable mobility practices, that in the project are responsible for the liaison with SMEs and startups embracing innovation in the public transport domain. With the urban mobility landscape evolving faster than ever, the use of satellite navigation technologies for geolocation of vehicles and users represents a key enabler for most of the new mobility services. Indeed, when moving around the city using different routes and means of transport, knowing your accurate position and that of the vehicle you are using at all times is essential. It is for this reason that many transportation bodies factor in geospatial technology when defining their urban mobility plans and public procurement processes. The incorporation of Galileo positively impacts all existing applications of global navigation satellite systems in urban mobility services, and more importantly, it will enable new ones. So what are the benefits of multi-constellation, multi-frequency GNSS receivers? First, the open service navigation message authentication is one of the most differentiative added value features of Galileo, as it has the potential to enable a whole range of applications that are not possible today. It allows the GNSS receiver to verify the authenticity of the GNSS information and of the entity transmitting it, ensuring that it comes from a trusted source. It will be a free of charge service planned to be available between 2022 and 2023. On multi-constellation, when buildings block the signal and reduce the number of visible satellites, the availability of multiple satellite constellations ensures obtaining a much more accurate final position by combining all signals in view. Regarding multi-frequency, it increases robustness of the position against mass market jammers because the interfering signal typically has a narrow bandwidth and the receiver can still calculate a correct position with the other GNSS signals in view. More so, it increases resistance to multipath and accuracy. And the well-known multipath effect, the strength of the Galileo signal, together with advanced code modulations, makes Galileo better mitigating multipath effects, especially in the E5 band, but also in the E1 band, where it's 2 times better than the GPS in the L1 band. So due to Galileo's superior performance in stringent urban environments and the fact that it is fully interoperable and compatible with other GNSS, the use of multi-constellation, multi-frequency Galileo-enabled receivers on board public transport or shared mobility fleets is the main recommendation that the ARIADNA project is sharing with the urban mobility community. Luckily, such receivers are widely available in the market today for no or marginal extra cost in comparison to GPS-only receivers. In this paper, we present 3 examples where Galileo has been successfully leveraged for a significant, measurable increase in the quality of the service provided. First one, Transports Metropolitans de Barcelona, the publicly owned company operating metro, regular bus, and tourist bus services in the city of Barcelona, back in 2016 renewed the onboard equipment of some of the buses in their fleet. The positioning unit embedded in the exploitation and information aiding system was also replaced with a mass market solution which integrates multi-constellation and dead reckoning capabilities. Some tests were run by the operator before and after replacing the positioning unit in order to compare the changes in performance. The tests were conducted while the bus was providing service in one of the city's bus lines, which makes the results a faithful reproduction of the situations faced by the positioning technology during normal operations. So the figure you see on the left shows position fixes recorded with a GPS-only receiver. It is clear to see how the GNSS signals computed by the receiver were many times off the limits of the road, while the figure on the right shows position fixes from the new receiver in the same segment of the route. The improvement is, as you can see, outstanding, with the receiver returning much more accurate position fixes. According to TMB, the positioning error in the most challenging sections of this road went from between 40 and 60 meters down to between 2 and 5 meters only. Regarding the shared mobility business, evidence of the benefit of Galileo can be found from the experience of a Spanish moped sharing operator. Again, back in 2016, in the context of the Horizon 2020 project called GMOTI, the company tested an onboard unit which integrated a multi-constellation receiver that also made use of EGNOS. The company had experienced some problems with the reservation process in deep urban environments that caused that when a moped was parked in a narrow street with high buildings on both sides, the geolocation provided by the old onboard unit was inaccurate and could sometimes lead the user to the wrong street. On the contrary, the data provided, thanks to the new onboard unit, proved to be acceptable both in terms of accuracy and integrity. The new onboard unit's position fixes, in red in the figure, were always closer to the road, to the actual road, than the old onboard units position fixes that you see in the figure in purple. There were also many more of them with the new onboard unit, showing not only a significant improvement in accuracy, but also in signal availability as well. One important factor that contributed to the accuracy improvement was the use of EGNOS, which reduced in a couple of meters the bias introduced by the system. The third application reported refers to a demand-responsive transport service provided by a company called NEMI for the metropolitan area of Barcelona and currently in operation. The test, which took place at the beginning of 2020, was split in two phases. The first one using a Galileo-enabled tablet and a second one using a GPS-only tablet. The tablet is used to navigate the driver through the route, which changes dynamically according to the demand, and to show users the bus position and estimate the time of arrival in real time. The analysis was made on a route, figure you see on the left, which was repeated many times by a DRT service during lockdown, when there were very few regular users and the stops requested were always mostly the same. In order to assess the accuracy of the receiver in each tablet, every computed position was matched to the nearest road, and its error, that is, the distance to the road, was calculated. The histogram you see on the right groups the number of error samples in the y-axis by distance in meters represented in the x-axis. Since the error samples from the Galileo-enabled tablet outnumber the ones from the GPS-only receiver as the error becomes smaller, it can be concluded that the multi-constellation receiver was able to provide a much more accurate GNSS signal. In order to support the adoption of multi-constellation, multi-frequency GNSS receivers, the ARIADNA consortium has developed a complete hardware and software solution that can be used to showcase in real time the difference in positioning performance between a multi-constellation receiver compared to a GPS-only receiver. This set, that we call the Galileo demo kit, is available to all stakeholders interested to evaluate the increased performance of Galileo-enabled receivers in their concrete applications. So do not hesitate to reach out in case interested. Thank you very much.